Hello, everyone. I am very excited, and a big thank you to our friends at SPE and, of course, at Anton Paar for giving me the opportunity to present to you today's talk. This is something that is close to my heart because I was groomed to love rubber formulations. So I'm there right with you. So today, again, like Deborah has mentioned, we are optimizing the carbon black content and process conditions for some rubber formulations. For those that are more familiar with the Brabender brand in the mixing world than Anton Paar, as some housekeeping, in 2023, it was announced that the Anton Paar Group from Austria acquired Brabender in its entirety. And yeah, ever since we are one family with yeah, and this is also where I moved. So Anton Paar and Brabender are now two pioneers with one mission. This is something just to as a teaser what you're going to see. There's some extruded rubber strips, some of our drive systems with extrusion technology and how it comes out. This is just as an appetizer for you guys to see what's about to come. But of course, we have some mixing tests as well. Yeah, so what is our as an outline? We have our motivation, our challenge. We have a couple of instruments that I wanted to introduce, some of the measuring concepts and results, as well as then our conclusion. So why are we doing all of this? Our lab scale rubber process equipment can help you with the research and development in a smaller scale, so you don't need to bother the folks in the production world, but you can give very valuable insights about the production processes and hopefully give them some insights on scalability. And the typical thing that happens is that someone sources a new additive that is allegedly the same but for a better price. And if you are in the R&D lab, you will be tasked with the challenge here. This is a bag of material that I acquired. It's like 5 cents cheaper a pound. So please make that happen. And yeah, that is then where you come to play. And then you're going to go to the laboratory and then try to make this, see if this works out to save the company millions of dollars. So I just have to, yeah. We also wanted to add that there's a new methodology, or not really new, but there's something that can also help you to identify the cross-link density with something like a dynamic mechanical analysis. And this is here the temperature scanning stress relaxation. This is another ASTM standard that you want to look out for, and that we're going to cover. Yeah, so obviously the challenges are quite apparent. There's so many different mixing systems and everything has an impact. So there's filler systems, as you know. Rubber formulations are I call it who makes the best split pea soup, so there's a lot of formulations for a lot of different functionalities, and everything has to be in perfect harmony for the right product that comes out. And obviously the mixers are also different, small between large, tangential between intermeshing. So we want to also talk a little bit about wear over time, especially in production systems that run 24/7. And obviously I want to talk about ASTM standards, where there are some that are just qualitatively comparing without really having a quantification system. And that leads to sometimes really wild differences in interpretation based on how you look at the sample. And then temperature control is one of the key things that you have to keep in mind and be aware of. So what we are going to use here, as you are familiar probably with the Brabender lineup of torque rheometers, this is the latest generation that comes from the Brabender brand, now part of Anton Paar Torque Tech. We are going to measure the torque as we are going to rotate and mix the system. We have like what we used for our setup was like an electrically heated larger bowl system, the so-called prep mixer. We used Banbury blades. It was a tangential system. It's not intermeshing, tangential rotors. We used like a 15:1 3/4 inch single screw extruder with a roll feed, a slight compression for the extrudability for the Garvey die that we later have. We also used, of course, a mill and some software options. And I want to introduce you to like a new system that is like, of course, now in the portfolio because Brabender is now part of Anton Paar. So Anton Paar has like a large rheology group, and in this rheology group, there's like a system that is called MCR, which is like a benchtop rheometer, but that can be equipped with a linear lower drive in order to also have the function to do dynamic mechanical analysis under temperature control. So it's pretty much like a full-fledged DMA system that comes also together with like a standard rotational rheometer. Very cool. Recently launched in the new series. So here you see what I'm talking about. On the right side, you see like our extrusion system with, again, our torque rheometer that measures the torque. And we have our mixer with like those tangential blades. In this case, focus on the blades that are like the sec to the left from your screen, which shows like our Banbury blades. Very nice for rubber formulations. If you have very hard formulations like natural rubbers, highly filled, we also can use those chem blades. They look like those are the sets on the left. And yeah, we have like for thermoplastic materials, other variants available, but our focus here would be on our Banbury blades. Obviously, if you go through like the drive units, what Brabender always, their claim to fame is that you have like an ecosystem that can do a lot of different things with just one drive unit. So obviously after you have like the mixer that you can see here on the top, you can also attach an extruder. So you don't need two motors. You do exactly the same one, but you just attach it. So, and yeah, this just gives you like an overview of like the technical specifications and just to you understand the concept, how you can have one drive unit with several solutions and several tests. The software, this is something that Brabender recently, before the acquisition, already launched, is like in a new clothing. It has the same functionality, but just is like in current age and time. And the most important part from that slide is like, besides that, we can do like different variants of like speed or temperature programs. We also have like a full backwards compatibility to existing wind mix and wind extrusion systems. So if you come from previous generations, because you still have that in your application lab, the new software can import the old data. And one thing that I wanted to highlight, because this is dear to me, especially for my rubber friends, the temperature control program. So instead of saying like, hey, I want the speed to be like always fixed, you can make it that the stock temperature, the one that actually measures inside of the bowl, you can set this to a ceiling temperature of say like 105 degrees centigrade. And then the mixer would automatically adjust the speed, as you can tell here, in order to like maintain that temperature. Very critical if you want to do it all in one stage with like your cross-linking agent that might be temperature sensitive to activation. So here you get like the most energy into the system at a constant temperature, because the system will control the speed and the energy put in based on what the stock temperature is. Very cool for consistency. Yeah, again, better overview, just shows you like a little bit of like the weight. 400 Newton meters is in this configuration the maximum torque. Which, little side note, when the Anton Paar world entered the Brabender world and was part of it, their rheometers, of course, are not as strong. So they're extremely precise downwards. You will see this in the next when we come to the MCR. But when we talked about 400 Newton meters, it was like they couldn't believe it. But we couldn't believe it that rheometers can go all the way down to 0.2 nano Newton meters, which is absolutely crazy. But yeah, now we have pretty much a very good spectrum from like almost not measurable to like very high. So here you see our 2-roll mill. It's a standard lab mill, nothing special except that it's very compact and extremely robust. What you see here, those are tungsten carbide coated rolls. So I had people by accident putting like in a brass spatula or a screwdriver, and there was not a dent on those rolls. Absolutely fantastic, extremely durable. This is an electric heated version. And everyone probably has a mill. So here, what I wanted to like go into later on when we go through the concept, you see like the Garvey die. This is an ASTM classic. It's 2230. You can already see by the low number from ASTM D20 for plastics. And it just gives you a qualitative analysis of rubber extrudability and your formulations. And again, we have a small rubber extruder with a roll feed. Yeah, and this is like the new flagship and the new standard in like benchtop rheometry. And this is exactly where I said 0.2 nanonewton meters and all the way up to 230 millinewton meters. But the important part is that this one here has an upgraded linear low drive, which is like sitting in the lower housing. And that can like then take the probe and actually like do an elongation. And of course can do this also by vibrating. So, and if you really want to blow your mind, you can have an oscillatory up, down, and left, right to get like the maximum data. But yeah, what you see here, it goes in combination with like our nitrogen cooling system so that you can reach temperatures from minus 160 degrees to plus 600 degrees. So we have like really broad variety to test your samples at the end or like see like how it behaves as it cross-links under strain. And yeah, definitely check that out if you're in the market for also rheometers. So what we did for our study, I will walk you through here our design of experiments. I give you a couple of formulations that we used. This was all in partnership with some of our friends that you know, work in the Akron area as like a contractor for like formulations. And so a big thank you here to my friends from Ace Labs. And Eric, thanks. So we also have like our, you know, we go through our, how do we prepare the samples? We have our TSSR concept that you learn a little bit about what cross-link density actually means. And again, according to a standard, we have our Garvey die, and then ultimately the results and key takeaways. In case if you're wondering why is there an absorptometer, the system that you see here, the single most important active ingredient in any rubber formulation is obviously the carbon black. And yeah, this is like a hallmark of like testing since decades, is the absorptometer, which is like also a small rheometer, like the big one, but just tiny, and dedicated to this standard. So in order to classify what is the oil absorption and how can you analyze the surface activity or structure of carbon black under if you give a constant lubrication oil to it. So what are we doing here? I picked, again, remember when I says someone from purchasing comes to you and hands you a new bag of carbon black, says their new source claims it's the same as what you always had, but it is again 5 cents cheaper a pound or less than that. They task you, make it happen and see if it works. So I picked like 3 different carbon blacks. This is all standard reference carbon blacks. So one is an N660, is something that is like middle of the road of its structure. I will get into this in a little bit later. Then we have an N326 and like an N683. One is like a very high structured carbon black, and the other one is like a lower structured carbon black. From the N660, we variated the loading. So we have 50, 60, 70 PHR. And from the other ones, we stayed with the high one. So we have one that we like a lot, where we have 3 different loadings, and we have 3 different materials that we tested at the high loading. So we used an SBR formulation. We have carbon black, zinc oxide, stearic acid, sulfur, and TBPS. I can add later the actual formulation in case customers or you guys are interested in that. I have that here just as an overview. So obviously for mixer, we started at, for mixer speed, we had 60 RPM, and then we lowered it after the filler addition. Mixer temperature, it was 80 degrees, and then 110 max. And typically we had like 8 minutes. We had a couple of dampening functions in order to like see a smooth curve. And in the curing, it was 6 minutes at 170 C. That was what we would normally do in a press. Oh yeah, perfect. I actually have the formulations right here. So again, this is for the N660. This is our like 3 different versions, the phases where we added, and just like a standard PHR calculation. So see here, this is the one with the 70, 60, and 50 PHR, and how the net weight then changes based on how much volume, net volume we have. And here are the formulations for our SBR, and with the high structured, this is like a standard reference black called F9, which is like an N683, and then also the other one with like the lower structured A92 from the current series, which is like an N326. I will get to this, what that means right here. So most of you that are rubber and carbon black power users, this is familiar to you, but I'm going through this anyways. So we see you have like carbon black is like an agglomeration of nanoparticles. So the particle size is typically produces the prime particles, and as it agglomerates, it first goes through aggregates and then into agglomerates. So you see here very neat, how this all comes to be. And then you can, based on the nomenclature, you have like different structures based on like how the carbon black agglomerate is like looking. I always compare this to like snowflakes in comparisons to golf balls. So high structure carbon blacks tend to have a better reinforcing properties, low structure than low structure carbon blacks, but durability might be higher. So high structure carbon blacks have also much higher oil absorption number, and low structure obviously then lower. This just as an overview. In case that you don't are yet familiar with like the concept of so-called industry standard reference blacks, this is just that gives you a list of all of them that are available. They are classified. They come from different companies that will be like, named then in this A, B, C all the way to H. And they all come with like specific statistical values for oil absorption. I highlighted the ones that we are using. So again, we have like one that is like a mean oil absorption number of like 71.4. This is all in grams per, in milliliters per 100 grams sample. So it's a relative number, and or like a specific number. Then we have like the N660, and we have like our F9, which is an N683. The one in the middle is the one that we vary. So as you might know, and as Deborah mentioned, I'm also quite active in our standardization community with ASTM. So you will find a lot of references to that, because this is like a wonderful thing to like talk the same language. And a big shout out to our friends at D11, which is like the rubber group, and of course D24 for like carbon black. So we use like our tangential rotors that you see here. They have like a couple of advantages, but also, you know, I like this because it gives us a lot of free volume. It gives us a wonderful distribution forward and backward, and they are very close to our friends that have like the original Banbury internal intermeshing mixer, just a little bit less shear. So that's why that is a very good choice for like your small scale mixing. So here, as you can tell, if you see like a standard torque curve, remember we have a torque rheometer. So we measure the torque, which is like applied over the time, and it actually tells you how hard is it to actually rotate those blades at the speed that we set. And the red curve here shows then the temperature. And as you can tell, because it is so steady, the red curve, we ran this with like a temperature stabilization program so that it automatically adjusts the speed. Yeah, this is here in our case, this was the N660, the middle of the road with at 70 pH highest fill. And you can tell definitely the different stages, and you can see this here. I added that. We had like a loading peak from the rubber. Remember, we get like different phases of rubber plasticizing. So we have like different sections where we add different ingredients. So we have our mastication of the rubber at the beginning to make it nice and smooth and flowable. Then you have phase 2 addition. You lift the ram. You really increase once you get the active ingredient and the torque and the temperature, because carbon black is a reinforcing agent. Then we reduce the speed in order to get it down, in order to have like a phase addition where you homogenize the stuff when you probably introduce your cross-linking agent. You don't want to do that while you do this at like max temperature where the cross-linking was already onset. So here's how this already looks like. You see like some of our typical samples, some of them already, some of them have to be cured, some not, but this was all prepared and then milled and then cut into strips. So we left some for our measurements, and others are like all ready for the roll extruder. Now to the concept of the crosslink density. So again, there's an ASTM standard for the temperature scanning stress relaxation, but the biggest outcome of this standard with this measurement is the so-called crosslink density. So crosslink density in elastomers refers to the concentration of chemical bonds connecting the polymer chains. And obviously that impacts then the mechanical properties, stiffness, elasticity, and toughness. And again, we do this here by having like the ability under temperature to like strain the probe and have like apply a constant strain, and we see how much does it relax over time while you're driving a temperature ramp. And this is something that we do exactly here. There's a beautiful application note from our Rio team from Anton Paar. I'm glad to like also forward this to you guys if you're interested. And this just shows you like the stress relaxation once there is like a material that is like exposed to a constant strain and the temperature changes. So obviously you have the strain, then you hold it for a specific time, and then you have like also the ability to like do the temperature ramp and see how much it then even changes until it rips. There's like a couple of abort criteria, but normally you have like the 90% crosslink as like a endpoint. So yeah, that is our overview of like, and again, the ASTM standard would be D8363. So this is a little video that I took, because now that we have like our mixing done and we have like everything that you understand what you can get out of this, plus our sample prep, plus our, now comes the Garvey die. So this is a little video that I took back then. So you see here our extruder running. We have like temperature is set to about like 100 degrees. We have our roll feed, and we're going to like set the speed of the roll feed in order to like make sure that we have like a constant fill. Small extruders are perfectly fine. Remember, you extrude cold, and normally you would like configure hot. And yeah, that is our Garvey die. Again, the geometry is defined by ASTM. And then, of course, you want to look how is the shape, how is the swell, how is yeah, the contour, and how true is it under those process conditions to the contour. So you see, I already had like a couple of like variability for like, I did like 15, 30, 45 RPM. And yeah, we checked then obviously the different samples, and you will get like an overview of that in a bit. Good. So besides the Garvey die that I will later touch base on again, we have the extrusion data. The extrusion data, the same torque rheometer that gave you the mixing curve, of course, now gives you a little bit more information because you have something like pressure transducers inside. So you see here, this is like our little extruder. It's like a map key. So you have like symbols for like that symbolize the drive, the torque, the hopper. In this case, it's a roll feed. We have a pressure gauge, temperature gauge, and then the die. And then you can add comments. You can set like your temperature profile. And then, of course, all of that will be like one printout at the end of the test, where you get like and you can compare then the data. And here you see this was like at the speed 15, 30, and 45. And then you can see how the pressure, the green line jumps, how the torque jumps. And obviously, as we put more mechanical energy into the system, our temperature is also slightly rising. With increased temperature, our viscosity typically drops. So yeah, bear with me. You guys are in for a treat. You're going to see a lot of black extruded samples. But this is all the point of this exercise, that you understand that there's like some downfalls to this method. And we try to like offer some solution of how you can quantify the qualitatively test. So again, our different 70 PHR samples of like the 3 different carbon blacks. This is exactly what I was talking about. I mean, again, I sit in the D11 committee, and we're still having a standard where there's like, this is literally the reference that is printed and probably copied like 1,000,000 times. And, you know, in our modern day and age, there's most definitely like a way to like probably improve that. But we have to, of course, make sure that, you know, there's dedication and devotion in order to like attack this project in the committee level. But if you are still using this like this, then this is, you have like some samples that help you to like rate your samples. And again, there's 2 rating systems. There's like rating type A and B. And then you always go by like swelling, edge, surface, and corners. And then you can give this from pretty bad to pretty good. And then you can give it like also here, edge and surface. You can give this like this rating. And it actually states it in the standard. A precision statement is not directly applicable, since both systems yield only qualitatively comparison data. Since no accepted reference value can be determined, there's no real bias. So again, take this standard as like a glimpse of like internal reference and like having something to like go with. But I show you how I did this in order to get like a quantitatively version of like a qualification system. Yeah, some of the results. Here we go. So the mixer data. This is everything from the middle down the road, the N660. Remember, we had this middle of the road structured carbon black. in like 70, 60, and 50 PHR, you always see like everything bluish color is torque, everything reddish color is temperature. So we see here that like the lightest blue is like the one where we slightly at like the highest torque. The other ones are like fairly identical. There was especially between the first two and not so much, but you have to be also considerate if the operator, and you see here the minimum, was able to fill this slightly early, this makes this shift. So operator bias has to be still considered. Temperature is pretty identical because we ran the temperature program. We can see here by the energy. So our software also gives you like how much energy in kilonewton meter or kilojoules is applied over the time. And this follows directly what you saw here with the torque. Because for you that have not been yet familiar with torque rheometry, the area, so the integral under the torque curve is your energy that you put into between 2 points of significance. If you then know your sample weight, you can also get the specific energy needed. Here, this is just visualizing this very nicely, how close the first two were, 50 and 60 PHR, and 70 PHR. Again, we have to be careful. No, sorry, the 50 PHR. We anticipated that the lab technician was a little ahead of time filling that. You will immediately see that because that literally translates here. There's no real reason why the lowest version has like the highest energy in there. This is now a comparison between the three different at 70 PHR. Remember, this was the second part of the test. And this is actually interesting. So we see like that the N326, the lowest structured carbon, the hardest, so to speak, and the N660 were similar, but something happened with the F9. And this is like, there was a change in loading speed because there were issues with like actually loading that sample. So you see that gray curve. It is an outliner. This has to be like repeated because, or like the others adjusted, we were not able to load it at the high rotor speed that we initially had for the other ones because of the low structure of the carbon. But this is also something that helps you in the lab to understand how to set the right mixing parameters. Because if there is something that gives you like a hard time loading it in your small mixers or even in the large mixers, this will brutally show you the truth with like this F7 or F9. And that explains why this curve is here, because we had like significantly lower torque because of the rotor speed. The other ones were like fairly identical. So again, we go to the test where we compare just the different load levels of the N660. So this looks a little convoluted, but just bear with me. This is our comparison data. You always see like the steps of speed here at the bottom. This is always like 30, 15, 30, 45. And you see this for all different. 50 PHR is blue, 60 is red, and 70 is green. 70, again, gave us a hard time. We had like a massive drop. This is what you see here is what happens if something with the roll feed is amiss. But we quickly recovered because there was probably the strip running out and not fed accurately. The important part is that you see like a tendency where it's stable and with less jitter. But the higher we went, and of course here the top curves are like the load. So we see because of some of our discrepancy, the 70 PHR was like the highest lubricated one, while the others were like a little rougher. This is now, again, it's not art, it's art of extrusion rheology. This is, we have again the three steps, but this is now taking in consideration everything at 70 PHR, but the high structure, the low structure, and the middle of the line. Middle of the line is our E9. So this is the blue curve, and we have like the high structure is like the red with like the highest pressures and highest torques, while we have like the low structure to be like the green. So we have like some interesting results, but again, highly the variability has to be like improved by like the feeding solutions. So I will go over this a little quicker because again, I have like quite a number of slides now showing, try to like understand how the qualitatively version can be made quantitatively. So again, if you look at the extrude, you see like some of the swelling and some of like the surface area and how sharp those edges are and how well defined they are. So here 45 45 RPM is too rounded off. You see this at the end. So in this, the 30 RPM sample is the best. So what I did, I just simply says, all right, for that set of samples, which one is the best? And then I always did like the same thing here. 30 RPM for me was the best. Here, the 50 PHR samples, again, I thought 30 looked the best, least amount of swelling still defined. So now we just did like, again, everything was like 30 RPM seemed to be the sweet spot. And I liked the one from 60 PHR the best. So now we go to like our F9. So with our F9.2 highest structure, we see the same thing. I like 45 in this case. And for the, oh, it's not N990, it's N326. So, which is like the A92. So here I like actually also the 45 RPM. Here the comparison between the three different carbon blacks at 70 PHR, and it was 30, 30, 45. So, and here's what I tried to do. In order to make sense of something that is so highly objective and not with any laser gauge or anything, just my eyes looking at it, I just gave this like a rating sum out of the 16. Remember when we were at the standard where you have like the 3 different categories, or 4 different categories, and you can give it a number from 1 to 4. So if each category has a 4, the best number that you can give a sample that is absolutely perfect is a 16. So, and then I went backwards from that. So we have like the different samples. Again, this is all for N660. And I highlighted the ones that I deemed to be best. And I deemed this to be best also based on like what was this rating sum. As an overview, I also added, because we measured this here, what was our cross-link density and what was our total energy of the mix. So, and we can tell that here, this was a little bit the highest cross-link density. Of course, we had at like the highest fill. There's more chances of links to interact with the elastomer chains if you have obviously a high load. And then I made this into a visual representation. Obviously, the different samples, the ones that I liked, obviously are the highest ones. And then we go through like swelling, edge, surface, corners. I did the same thing here for our 2 other carbon blacks. Unfortunately, here the samples were, I did not have enough samples to get to that cross-link density. But we saw like the total energy that here actually the A92 had like the fairly high mixing energy. And remember, with the F9, we had to reduce the speed. So that's why the total mix energy is like lower. So this is also, please consider this with like, as like not being under the same conditions. But the extrusion results were like fairly good. So the one with the highest structure, the F9, even though we had like the least amount of energy, what did us a very good job for like how it was the extrudability. Same thing again, swelling, porosity, surface edge. And yeah, and then I did like a result matrix, which then hopefully can give us then, so to speak, the winner if you want to like see which one you would like to have if your objective is surface edge, swelling, and you know, appearance just from the extrudability. So we liked, even though it was the least amount of energy, we had like the best results, even at like a fairly high extrusion speed of our F9 highest structure N683. And yeah, as a conclusion for us, I wanted to like share obviously that the systems in use are like a very neat setup in order to like combine a lot of different aspects what comes to place. So the prep mixer for like understanding the mixing process and measuring the energy and like keeping the mixture homogenized under temperature control. Garvey dye, obviously, maybe not the best method, but a very simple and easy to understand method to give you a qualitatively gauge that you then internally can quantify. And quite frankly, there are probably like systems out there that can also measure this as like a geometry now with lasers. But for now, the standard is as it stands. This really helps you. So this whole setup and everything that I presented was like 2 days work between mixing and yeah, maybe 3 because we had to clean too. But you know, the formulation development can really quickly gauge you which one of those carbon blacks are like the best one in order to like give also your production team, if you want to improve your formulation, maybe you can, you know, revert to this one. Obviously, our platform is like a very useful, versatile platform to handle all of those tasks with just one drive system. And the TSSR, in this case, our Anton Paar rheometer, gives you like a great ability to like judge the crosslink density and give you like valuable feedback about like how many crosslinks in your formulation have been formed to get you like another set point in your decision matrix. And then obviously you would probably see the results also in the mechanical testing and other values that the DMA gives you. And yeah, there you see the young version of me. And this is just something for you. And I am extremely happy that to hear questions that you guys have.
Thank you. Let's take some questions from the chat window. First question, what needs to be considered regarding the equipment if you want to use reclaimed carbon black RCBs?
Oh, all right. So with reclaimed carbon blacks, there's an entire new committee. This is called D36. This handles the reclaimed carbon, and I think their not codex, but their scope already says that reclaimed carbon black can have up to 20% of non-organic fillers in the reclaimed process. That can be anything from nails to sand to stones. So as you can tell by already what I said, this is normally not something that you want to have in your mixing equipment or extrusion equipment, especially the stone parts that can be very hard. So you might need to like armor up. Some of those equipments are already fairly substantial with like nitrided steels or like extra armored ones, tungsten even. And that would be my recommendation. And reclaimed carbon blacks have like, because there's like this variability, the results might highly vary. So I would tend to like run some extra tests before that. And the crosslink density and especially also the oil absorption shifts significantly because again, the structure of the carbon might be less. So there might be less entanglement points. So please be mindful and always test, and probably a blend of two would be the best so that you have virgin and reclaimed. But reclaimed, of course, has the charm that is really affordable. It's a really good argument to test this, but please be mindful of your equipment. Make sure that it can handle potential non-organic fillers that are hard and scratchy, because you might we ruined an absorptometer mixers in 3 tests because there was so much sand in it. It was completely scratched up. So be mindful of that.
Next
Yes.
question. ASTM D3182 suggests a two-stage process to keep the stock temperature at bay. You did all in one. What can be done to control it this way?
That was I explained some of that in in our temperature profile. This was where you saw when I explained that we have like a temperature control program where we adjust the speed. So I would recommend to always activate that in order to get like mixing consistency and energy input. Then you can skip the part where you just like take the green sample out, put it on the mill, and add the sulfur later. But of course, your version of how you do things do not necessarily need to be a bad one. This is just something in order to maybe streamline this to have like a better incorporation, that you do not have pockets of sulfur that have a high crosslink, and then others where you have like lacking, because you will see this then in the mechanical properties. So activate that program.
Next question. If you use a natural rubber and hard carbon black formulation, the torque spike can break shear pins easily. Any thoughts on how to avoid that?
Yeah, so the latest versions of like torque rheometers, they come with like they know before some of the stuff happens from like the software version, and also the motor controller has like a built-in version in that. But we can also set in the software soft alarms where you have like pre-indicators if you go to that, and it can automatically adjust then the speed, because the speed is the one that typically brings your formulation or like brings your system to the limits. You can like adjust that so that automatically when you reach, for example, 360 Newton meters and your maximum is 400, so take 10%, which is 40. So set it to like as a caution alert at like 360, and then say like reduce speed to like 70. The second you take speed off, the torque will go down. I mean, of course, you sacrifice energy, but it is better that than breaking blades, or, I mean, shear pins cost nothing, but I'm just saying it's better safe than sorry.
Next question. Low RPM or higher RPM, which one is better?
Wow, this is really, again, a formulation dependent question. You saw in my Garvey dye experiment that with some of the material, it actually liked the higher RPM because it liked the higher shear, created like a lower viscous material that was shaped. And in that case, it had enough structural integrity that it was not bulging and not swelling. So, and in this case, again, it seemed to be like, based on the results that I had, that the formulation from like that had the highest, that had the SRB F9, it was actually able to extrude at a higher speed, while the harder ones, they like the lower speed, because the elasticity plays a key role. So if you squeeze something that does not want to be squeezed through like a surface, there might be even more swell. So yeah, uh, the to give the best answer is just look at the data that you generated. And that was my takeaway from our little design of experiment. So, yeah.
Next question. Can carbon black and polymer material be used?
Can you repeat carbon black and what was the other one?
Can carbon black and polymer material be used?
Um, well, carbon black is a common colorant or pigment for polymer. So we have companies that use carbon black as like an additive for color the entire time. If this is more like towards like thermoplastic vulcanized elastomers, so TPEVs, yeah, you have to like consider that there's like the elastomer phase that creates the cross-linking and creates this haptic feeling that you know from like some of the higher end screwdrivers, where you have like a TPEV that is built into a matrix of like with thermoplastic material. But yeah, absolutely. I mean, we had even a method created at the time when I was at university, where we used an internal mixer instead of a twin screw extruder to create TPEVs, where we melt at very high speeds the polymer matrix. It was polyethylene in that case. And then we would add some of the chunks of like it was an EPDM that we then just cross-linked in order to make a TPEV. So if you make a hybrid, yes. If you have just pure thermoplastic material, like a normal polymer, like it's polyethylene, you can use carbon black as a colorant, and it's not really going to reinforce it. It would be like more, giving it a different appearance.
Okay, and then those are our questions. Thank you for the lightning presentation. Do you have any final comments?
No, I want to thank our community and everyone at Anton, Paar, and of course at Brabender of like being trusted customers for such a long time. And whenever you have questions, please reach out. We love to share what we know and how we can help you.